TTL Computer II. Today, we're going to take a look at our clock circuit board design and the PCB that I've been able to put together. Okay, so we're just going to jump into this. So first thing I did was we're going to start off with our digital simulation again. So this is our clock circuit, and I updated this again. So I changed this all over to use tunnels rather than traces, just because I started to do the circuit layout, and it's easy to get confused with the lines, the trace lines that we had, because there were a lot of them and crisscrossing. So it's just easier to use the tunnels and validate that the wiring is done correctly for when you have a lot of tracks. So that's what I did here. And I also did it so that I could, validate that in the simulator that the computer still runs and that the tunnels were done correctly. So that was my first step, was to update that. And then we're going to jump into the circuit design. So this is, again, I'm using Easy EDA, and this is our schematic. So we see that we have, our elements that we carried forward from our digital design, our LS714. We have our two D flip-flops, and then our 245 output. And then now we're starting to flesh out the schematics, and we have to be very specific about our designs. We're not in digital where we don't have to worry about a lot of electrical things. We got to take care of all those details now in our schematics. So this is our oscillator that's added, is a 4 megahertz oscillator. Here's our little power indicator light. We have an LED with a current limiting resistor. Then we have over here, we have bypass capacitors, 100 nanofarad bypass capacitors that we use for all of our ICs. I have three 100 microfarad decoupling power capacitors that will be added to the board. Here also is our backplane connector that we're going to be using. And we see that we have our P clock, our not clock, P clock, U clock, T clock, and clear signal are wired into the connector. We have power and ground for our board coming in through the connector. Now, I'm also some other like housekeeping things. So you can start to use that. We use these 33 ohm resistors mostly for everything that's driving the backplane. And those are for two reasons. Those are impedance matching resistors to help match the impedance of the tracks in the backplane. And the second function there is that they are to help absorb signal reflections in the traces, and also going to the backplane. So what happens is when we have the signal, traveling down the trace, it reaches the end of the trace. Some portion of that signal reflects back down the trace again. And these 33 ohm resistors help to, dissipate those bounce back signals. So we use those mostly going to the backplane, and that's what this is here, is a resistor network, a 33 ohm resistor network going to the backplane. But this is our high speed oscillator signal, all right, our main trace going to the D flip-flop. So we're going to use that 33 ohm resistor there to help absorb any of the signal reflections there. Okay, so that's our completed schematic. Now we can go and take a look at the PC board design. Okay, and this is our PC board design. So we can start to see this is our board layout. We have our backplane connector down here. We have our D flip-flops. We have our oscillator and our 74 LS14 here. So we can start to see that we have, here's our power indicator. And we've laid out also in position the bypass capacitors, here, here, one for each IC. Bypass capacitors here for this IC. For our 245, we have our bypass capacitor. And we also have our decoupling capacitors here, the 100 microfarads here, and down here where the power comes in from the backplane. We have a decoupling capacitor and another bypass capacitor here. Okay. Now, and then we have our main signals coming into the backplane, right? The NOT clock, P clock, T clock, and U clock coming into the backplane here. So this is our top layer. We can see here, this is our bottom routing. Most of our routing goes through the top. Some goes through the bottom. So we can, one thing to note here is, all right, so this blue area is a copper, what's called a copper pour. And that is just a copper layer that's added to the board, and that's connected and provides, this is our ground plane. So one thing to note is that the ground plane is pretty contiguous, and there's not any real breaks in the ground plane. That's desirable. Let's go back to our top layer here, and the red layer is another copper pour, and this copper pour is for VCC, and this provides our power plane. So we kind of have a sandwich. We have our board in the middle. On the top layer, we have a power plane, and on the bottom layer, we have our ground plane, and those two things kind of make a big capacitor. So that helps to stabilize our supply, power supply to the board. Now, one thing that you might be saying is, well, what are all these blue dots all over the board? So those are something that's I didn't really know about before I started doing my board, but they're called vias. And what those vias are is really like a little copper tube that goes from the bottom from the ground plane up to the top layer of the board. It's not connected to the power plane. We see that there's a void there, but that is like a tube that goes right down to the ground plane. And what those function as is kind of like little antennas. So with the signals on the board and the traces, we can get like all of these eddies of current in the board. And what these vias do, act as little antennas to absorb all those stray signals that occur on the board. And so that's what they're there for, to really to clean up, improve the signal quality on our board. And so I've used two techniques to place those. One is just a grid that puts those all over the board, but also I have placed vias in key locations, one of those being here. So this right here is the trace of our main 4 megahertz signal from the oscillator. And this via here is placed right next to that signal to really absorb any stray signals that come off of that line. And here, these vias also, they're a key element in PC board design. Look up return path vias in Google, and you'll find tons and tons written on it, and is a key design element for signal quality and in your boards. And I have placed those vias in key locations here. Again, these are our main signal lines, NOT clock, P clock, U clock, and T clock. I've added return path vias there. And I've also, same thing on these signal lines, return path vias here, and also connecting to our connector, return path vias here. So those are a key thing that I really didn't know anything about, again, before I started this process. So it kind of seemed evident to me that, again, this is my first effort for PC board design. And I really got the sense that I skipped over beginner and went right to intermediate. And it's pretty evident that that was the case here. But now when I did the routing here, I placed the components on the board manually, and I arranged those to something that gave me like a good starting point. And then I did auto trace routing, and that was okay. But I ended up doing maybe 50 or 60% of the routing again by hand to get to what you're seeing now. And yeah, you're pretty much recommended to do manual routing. When there's a lot of lines, traces going all over the place, it's kind of hard to do. But I'll probably do that on my next board again, do automatic routing, and then fix it up with manual routing for important traces. But we'll see how that goes. For something like the back plane, the back plane, the motherboard, I'll probably do manual routing for the whole thing. But I don't know. I'll try and see if this combination of auto routing and then going back a second pass and doing manual routing, if that works when we get to my next board. But okay, so let's take a look at this is our bottom layer. I think we looked at that. Here's our bottom layer, and we can see that there's not too much routing on the bottom. And again, this is we see that this is all continuous and unbroken ground plane. So that's highly desirable in our board designs. Okay, let's look at our 3D view. And this is our 3D view of our board. And we can see, get to rotate this around and see what the board is going to look like. A key thing here that I wanted to do was, inspect the edge connector to see how that lines up, and we can really zoom in there and see that it's just past the edge of the board. There's a little bit of a space, and I wanted to keep that there. I didn't want to be too close to the edge of the board. So that looks pretty good. And we can see we have the outlines for all of our components, and we have labels for the components, what they are. And yeah, I think this came out pretty good. I'm pretty happy with it. And I'll be ready to submit this to fabrication today, which I will do at some point today after I finish this video. But hey, that's it. I said this will be submitted for fabrication today. And then I'm going to jump into doing the circuit design for the testing board or the testing jig that I'll be using for all of the printed circuit boards. And that'll be my next effort. But and I'll do a readout for that board as well. But and that's it for today. Until next time, that's it. Thanks for watching.